using magnetic compass like a galvanometer. When magnet is moved over or inside a solenoid, a current gets induced in the coil of solenoid. This is called induced current. This happens due to change in magnetic flux or magnetic field lines. Today we will do an activity to show this induced current using a magnetic compass. We will need a magnetic compass, laminated copper wire from soil to black choker motor, two rubber bands, a homeopathic coil made of plastic. On this homeopathic coil, wrap the copper coil one by one around 800 to 1000 turns space between the two rubber bands on this coil. This 800 to 1000 turns will make a powerful solenoid. Also needed is a big cylindrical near diamond magnet. I didn't have any, so I combined many small near diamond magnets. After that, I wrapped 5 to 10 turns of copper coil on the magnetic compass. This will act like a galvanometer. These are the two ends of the copper coil, and the north pole of this magnetic compass will act like a needle of galvanometer. In order to check the polarity of my near diamond magnet, I bring it near the needle of magnetic compass. This tapering end is being attracted towards the north pole. So this is the south pole of near diamond magnet. The tapering end is the south pole and other is the north pole, like this diagram. In order to calculate the minimum distance beyond which the magnetic effect is not felt by the magnetic compass, I bring this near diamond magnet near magnetic compass slowly and moving, so that I can calculate this minimum distance. And on watching carefully, I find that approximately 1 feet and 4 to 5 inches. This distance is approximately 1 feet and maximum 5 inches. So beyond this distance, this near diamond magnet is not affecting this magnetic compass. As you can see, I have made the circuit in which the distance between magnetic compass and solenoid is around 2 feet, just less than 1 or 2 inches from 2 feet. Now to start the experiment, I move this magnet over solenoid and look for change in the needle of magnetic compass. South pole is brought near the solenoid. The deflection is towards right, back, again right, back. As I move the south pole over the solenoid and turn it away, the deflection in the magnetic compass is right, back, right, back, right, back, right, back, right, back, right, back. Again look carefully, the deflection is towards right, back, right, back, right, back, again right and back. In order to check from the other pole how the magnetic needle's deflection is there, I change the polarity of near diamond magnet, I reverse it and move it over the solenoid like this. Now the deflection is, look carefully, the deflection is towards left and back, left and back, left and back. This happens because when I bring the south pole of the magnet over the solenoid, then the end near the south pole also becomes like a south pole due to Lenz's law, and the end becomes like a north pole. So as per the right hand rule, the south face of the solenoid and the north face of the solenoid have currents in opposite directions. The north facing side of solenoid will have current in anti-clockwise direction, and the south facing side of the solenoid will have current in clockwise direction. The north face will have an anti-clockwise and the south face will have in clockwise. So this side of the solenoid will have in current having clockwise direction and the other will have an anti-clockwise, and so the current will flow out and it from the solenoid in clockwise direction towards the magnet like this, and therefore deflection is towards right. So when south pole is moved from right over the solenoid, the deflection is towards right, and when it is moved away, the deflection is back towards the left. Now when I change the polarity of the magnet, the north pole is brought near the solenoid, then this end of the solenoid which is near the north pole becomes like a north pole, and the other end becomes like a south pole. So in this case the direction of current is reversed and it becomes an anti-clockwise direction towards left. So the deflection is towards left, then again back to right, then left and again back to right as I turn away the magnet. Now let us try to understand this activity from pen and paper. This is the solenoid and this is the magnetic compass which I have used in place of a galvanometer. They have been connected, and this is the symbol of near diamond magnet. When the south pole or the tapering edge of the magnet which I had used had been brought over the solenoid, then this face of the solenoid becomes like a south pole also, and it repels this, tries to repel this magnet, sort of repel this magnet, because according to Lenz's law, the induced current will be flowing in a direction such that it opposes the change that produced it. Now here the change is in the magnetic field lines or the magnetic flux of this magnet. When the south pole of this magnet is brought near this end of the solenoid, there is change in the magnetic flux, and due to this, here also a sort of south pole is created which opposes this magnetic field, and therefore the current flows in this direction. The induced current is in clockwise direction outside this solenoid, because from the right hand thumb rule or Maxwell's screw rule, we gathered that if a current is flowing in upward direction in a conductor, then if I look from above, the magnetic field produced around that conductor is in anti-clockwise direction, and if I look from below, the magnetic field will be in clockwise direction. Like this, if I hold this pencil from like this, so my thumb is in the direction of current, and if I look from above, the magnetic field is in anti-clockwise direction. If I look from below, the magnetic field is in clockwise direction as per my fingers are crossed. Therefore the induced current will be in this direction, because this side of the solenoid is acting like a north pole and this is like a south pole. So current will be in like this. This is in anti-clockwise, and from below it is clockwise. So as we have learned earlier, this will the current direction outside the solenoid will be in clockwise direction, and the galvanometer needle will deflect towards right, or magnetic compass north pole will deflect towards right. So when south pole is brought here, the deflection is towards right, and when it is moved away, the deflection is back to the left. Let us look at the other case. When we had brought the north pole near this magnet, then if we bring the north pole this solenoid, then this face will act like a north pole and this face will act as south pole due to Lenz's law, because induced current opposes the force producing it. So the current will be produced in this direction from right hand thumb rule. If this will act as north pole, then this face will be having anti-clockwise and this will be having clockwise direction, and since the clockwise direction is looked from below, so this will act like this will be in this direction. So outside the solenoid, current direction will be in anti-clockwise direction, and deflection of galvanometer or magnetic compass is in left, and when this north side of the magnet is brought away from the solenoid, the deflection is again towards right, back to right. Thank you.